Hello everyone. Yes, thank you. A huge thanks for Alex to have invited me to give this talk, and huge thanks to organizers for putting up together this great opportunity for us to share some nice ideas and people present their results. In my case, yes, I would like to have a. So first of all, everyone sees me and hears me well, right?
Yes, it's fine.
Yes, absolutely. I will be really delighted if you guys can, if you interrupt me, you ask questions, you try to participate. This will be highly, highly appreciated. There is certainly no continuous flow of what I'm saying. So on the contrary, if I can clarify something, it's better. And in fact, it's also nicer for me as a speaker, because in practice I don't see anyone. I don't know any reaction. I don't know how I'm actually doing. You just see my screen. So in that sense, it will be nice. So okay, so let me share my screen, because what basically, right? So people see my screen right now, right?
Yes.
So what if if I do that full screen, is this better? Should I make it bigger?
Yeah, it's okay both ways.
Yeah, the text is sorrowful, right? If you need the size of the text bigger, please let me know. Anyway, let's start with our with this workshop, which will be about differentiable programming for particle physics simulations. So yes, I'm a researcher at NIPT Nuclear Physics Methods Lab. Just about actually to start, hopefully. And also I'm CTO at GrinisRIT, which is a company developing simulation data analytics software, in particular some open source software. And actually the code you're going to see today is available in a repository called NOAA, which is a set of basically Bayesian computations, very nascent project in C++17 over Pytorch. And I also would like you to keep an eye on KMAT, which is a really wonderful library we're working, several people from the Nuclear Physics Methods Lab work on. It's a Kotlin library in mathematics, and all of the Bayesian computational algorithms and all those things will appear there. And I would like also to, on this occasion, thanks JetBrains Research for actually supporting us in developing KMAT. So yeah, it's a great pleasure. So keep an eye on both of those projects. Yeah, I don't know. I've seen a lot of. I've seen Oliver Schultz speaking at this conference. So maybe there is a fan club from Julia coming in. And obviously, I would like to take this opportunity to actually say that we will be really delighted to kind of find some connecting points or collaboration ideas, and yeah, and expose some of those algorithms to Julia as well. So just yeah, let's move forward and keep in touch on those things. So okay, what is differentiable programming? So that's a somewhat of a maybe buzzword, I guess. It's getting a bit of a buzzword for particle physics. So by differential programming, hopefully by the end of this tutorial, we will have a nicer view of what it is. But in practice, it's really a way to write your software in a way that basically the calculations you are doing, the functions you're applying, they pick up derivatives. So you can take derivatives with respect to the parameters you're using in your calculation, and the derivatives are calculated basically automatically by some engine. So there are several approaches to differentiable programming. I guess the most common one is automatic differentiation. You could also, of course, have things based on symbolic calculation. And actually, in our lab, Nuclear Physics Methods Lab, there are quite a few people interested, in particular Yaroslav Postovalov. has recently produced a nice paper that I all advise you to have a look at on symbolic calculation. But yes, so this workshop is about having a look at how this can be applied. This automatic differentiation ideas can be applied to problems of simulations in particle physics specifically. So why, in fact? So the first answer to this why question, well, because recently we got we got some nice automatic differentiation agents popping up. So people are obviously, this is quite an old idea, but recently we really have some frameworks which are really powerful enough to actually give some to handle really heavy computations. And what I have in mind is basically frameworks coming from machine learning. And in fact, as an example of a differentiable program, you can think of the neural networks in deep learning. So this is basically the most common and basic example of a differentiable programming routine. I would like, however, sort of so here I hope I will provoke a few people. I would like to distance myself a bit from machine learning and deep learning in the sense that it's a fabulous area of computer science, but I'm not quite convinced, and I don't quite see where its place is in computational physics. And that being said, I think that there are a lot of computational tools. Well, apart computational tools, there is also progress in data engineering and in visualization, and I all would like to invite you to have a look at what Alex Nozick is going to talk tomorrow about the wonderful visualization library. But yes, so machine learning make progress in software for analytics and numerical software, and in particular, machine learning pushes development in areas such as automatic differentiation, because that was what was the real success behind this deep learning boom, and also computations on GPU and optimizers based on gradient descent. So a lot of things that have been moved forward. In that sense, actually, I think that physicists, even before we had any idea about computers, they were already using techniques of curve fitting, and beyond using curve fitting, they're also interested in gradient descent methods, and obviously they are also, as I hope to convince you, interested in automatic differentiation, but that has little to do with machine learning, in fact. So, and yeah, in that sense, if someone has a more sort of counterpoint view to express regarding what machine learning is doing in physics, then please raise your hand and have a shot. But yeah, I think that computational physics should focus and should use the tools that are produced by this machine learning community, software developers and data engineers, to actually solve problems, but not the actual machine learning theory. It has nothing basically to do with what we're doing in physics and in science in general. So that being said, I also would like to mention beyond TensorFlow and Pytorch, which are moving a lot away from just basically taking a cut and trying to guess that this is a cut. They are moving to actual fully numerical libraries where they're first of all backed by powerful linear algebra libraries like Intel MKL or QBLAS. They also offer you the way to run your algorithms and actually, if you're if you stay within the philosophy of those frameworks, you can write your code such that it exploits GPU and Cuda, and I'm gonna show a few examples today. Yes, and also, of course, the cherry on the ice cream, so to speak, is the automatic differentiation engine that became quite powerful and allows you to solve hard problems. Again, expecting people from Julia being around, I would like to mention maybe Flux and Zigot. They also have nice tools. There maybe Oliver is going to talk about that in his workshop.
Sadly, they are not still around, but we will be sure to ask them tomorrow during their talk.
Absolutely. So let's. So what is so another answer to the question why differentiable programming now for particle physics? Well, because recently we had a few interesting papers coming from Ricky Chan, and on using basically the joint sensitivity method from ODE solvers, which goes back to the I don't know, it goes back to really long time. And then these ideas have been also picked up by Chris Rakokos and his collaborators, and they sort of and they produced actually a Julia package called Defect Flux, and Chen produced Torch Defect, which is a Python package over Pytorch. There are also now TensorFlow implementations and all sorts of things. So basically, what happens is that so for when it comes to mathematical modeling, so when we sort of model our when our models are expressed in terms of ODEs, PDEs, stochastic differential equations, then in all of those situations, we actually have an idea on how we can compute the gradient of a solution to those equations. And exactly those ideas actually kind of went to complement what has been implemented in Pytorch and TensorFlow and those automatic differentiation engines about and actually improve the way actually they compute, in particular, gradients for recursive neural networks. But on the other hand, because we can compute the gradients, here we come to an interesting application, is that we get more tools to approach essentially inverse problems in physics. So that's different from machine learning. So I love solving inverse problems. I don't like curve fitting, but inverse problems, they are different in the sense that your theory, your computational theory is absolutely fine. You're not trying to test it, or what you're trying to do is that you have a few parameters in your model that you actually don't quite know what they are, but then you observe some data coming from your experiment, and you basically want these parameters to sort of kind of fit optimally or infer something about those parameters. But this doesn't touch necessarily physics as they are or any physics law. We are completely happy with the way we model the whole physical process. And in that sense, yes, of course, we can compute gradients of solutions of ODEs, but the problem is that typically those parameters want to describe, say, some density, which is a sort of a very high dimensional object, because at every single point in your 3D space, you can have different density, and you probably want to exactly, you should think about tomography in some sense. And you want to kind of, you have your sort of flux of particles going through this density, and you try to infer something about what the density is given what you observe in your detectors. Actually, I should say that in my research interests at the NPM lab are mainly about myography, and I'm kind of gonna sort of come up with this sort of example over and over again in my talk, because that's what actually the main motivational, my main motivation to develop these things. But of course, it is a much bigger application than we think, than just myography. So, and you want to infer something from those, and a good automatic differentiation engine would enable you to sort of parameterize this density in an interesting way, and then compute efficiently the gradient. Because obviously, when you take the gradient of the solution, at some point you're going to take the gradient with some of the inputs, and then this should propagate down to the way you try to parameterize the parameters. So it's a sort of both ways complementary, fruitful interaction between say what has been done in machine learning from the computational point of view and what we already for years knew about solutions to differential equations overall. So GrinisRIT actually built a really big framework, I think, which they can solve all sorts of problems. Ricky Chan's framework and his collaborators, of course, there are many people, obviously all of them deserve mentioning. They sort of focus more on the ODE, but also there have been some sort of more packages in Pytorch coming up. But I think the one by GrinisRIT is and his collaborators, the defect flux, is kind of the top one in terms of tooling. And if you want to have a try, then you could have a look at that. What I would recommend you to kind of use as a first shot, to have this sort of more data-driven approach to solutions of differential equations. Let me also mention computational finance. This is partly because my background is in computational finance. I spent a few years in the industry before trying to do some physics now. But it's interesting to mention that there are obviously some roots here. In computational finance, basically the point of view is somewhat a bit different, because here they also so they have a well-defined actually model from the point of view of theory. So they have a market with no arbitrage, and so they sort of in this market they price the various products. Then they go to the market, and the market typically will tell them what they believe the price of this product is. And from the business point of view, it was always very important to have to understand to have actual values of the derivatives with respect to the parameters of the model that goes into the simulation. So a lot of people in computational finance very early on started to think, oh, okay, how we can efficiently compute gradients of functions that we actually simulate. So we don't know exactly the value, we have to simulate them, but how can we compute the gradients without doing all this sort of bumping? By bumping, I mean finite difference computation of derivatives. I can tell you that in the industry, despite this interest and Mike Giles and his collaborators making a huge progress on this area, and I sort of obviously invite you to have a look at this, for example, survey, which will give you more references, because in some sense it's actually quite close to simulations that we will do in physics. So just from an idea point of view, but essentially Mike Giles, I haven't seen this being used in the industry. The main reason, I guess, was that 2011 it predates the development of TensorFlow and Pytorch in some sense. So at that time we simply did not have powerful enough automatic differentiation engines. So that was the complicated part to make it actually applied. And so basically, probably if some of your friends or you had the experience working in a large investment bank, you will be still doing finite differences. But today, it is, I think, possible now to have automatic differentiation for simulations, and specifically for simulations. And this is what we're going to discuss, of course, from the physics, from the physics point of view. I should say, yes, I'm new to the physics community, and I have looked quite thoroughly to the literature, mainly from the myography point of view, and I haven't seen a lot of ideas in the literature about how you could go about applying algorithmic differentiation to simulations in particle physics. So I sort of consider that this is somewhat of a new addition, a new point of view.
By the way, I can add from the physicist point of view. There is a field where there is a problem which was solved with analytical differentiation for a long time in physics. It's a calculation of tracks of particles in the accelerators, because they use analytical frameworks like Mathematica for that. Yes.
I mean, this is used, but yeah, I'm really talking about the actual simulations. Well, in any case, we will sort of have a look at it more in detail about what I mean. However, I would like to mention, yes, thank you, Alex, a lot for dropping this this interesting comment. I would like to tell you that in some sense, compared to ordinary differential equations, of course, and to what we do for what is done in computational finance, or compared to even solutions to partial differential equations, which are really complicated to set up, still the simulations in physics are much richer, so they're much more complicated to deal with than just simple ODEs. However, amazingly, there've been also a lot of development, which actually just kind of tells you, yes, that's the way to operate. Like we want, so the joint sensitivity method just, so basically you have all the tools you need to have a proper joint sensitivity method implemented in particle physics simulations. For those simulations for which you can actually run something called backward Monte Carlo. So again, I'm coming from myography, and we will talk a lot more about backward Monte Carlo in a moment. But this is where I sort of seen a lot of tools have been already developed and even implemented. And in some sense, the situation is more complicated than in typical differential equations or finance simulations. But on the other hand, there are really great tools like backward Monte Carlo and that have been already developed and are already there. And it is in fact possible to make this connection between automatic differentiation as we know it in machine learning and the differentiating results of a physical simulations problem. So yes, so let's move forward. And regarding the code, actually, so I will be working over LibTorch. I should actually say that I love LibTorch, but I don't have any. So I'm not working for Facebook, and I don't have any. So I don't have any lucrative reasons for me to sell you LibTorch. So obviously there's no clash of interests here at all. It's just that I love this package and I'm trying to use it a lot. And obviously over this tutorial, maybe I'll manage to convince you to kind of move your calculations to Pytorch as well. But there is no lucrative interest for me in doing so. Just to mention, because sometimes you're paid to promote something. So one reason I like a lot Torch is because you can, so I'm gonna run some of that stuff. So this is just for this piece of code is not very interesting, but Torch has a really nice. It has a. So what is libtorch actually? Sorry. So libtorch is actually C++ front end to the Torch C++ backend. So as TensorFlow and as many deep learning frameworks, they all sort of typically have a C++ backend, which is really hard to work with, typically extremely hard to work with. But Torch, compared to other competing platforms, I think, just I think a couple of years ago, essentially, have launched themselves into C++ and have built a really nice C++ 14 front end to their to the whole framework. They actually did even more because they sort of improved the backend on the way. So you actually have now a much nicer C++ backend to have a look at as well. And there is a real, genuinely seamless integration between the C++ code and the Python code. So in fact, you can easily prototype and play around with Python, and then it will be very easy to translate your code to C++. At the same time, you can write in C++ and easily integrate it into on the fly, essentially. So that's what this load function is going to do for us. In a moment, I will tell you a bit more. It enables you to load C++ code and just play around with it in Python with no problem. All of that still happening. It's a genuine, actually, C++ front end, so you actually genuinely drop the GL from Python, and so that's important. Now, you can tell me, okay, why now are you? So, for example, here I have written some of those extensions. I'm gonna, when time comes, we will obviously look at what has been written here. But here, for example, so it takes this C++ file and it's just going to compile it, and you can compile C++ 17 if you want. That's what I use, and you also can extend Torch very easily with Cuda kernels as well. You can add all sorts of files. You don't even need to know anything about Ninja or CMake or Make. If you stay within the Pytorch sort of ecosystem in your C++, then you will be able to easily. So this executes so fast because actually I already compiled, obviously, the whole thing. So when you sort of call it again, it's just not gonna. But you see, it's a similar situation when you can write C++ code and bring it to Torch. And yeah, later I will show you a bit more examples. So let me again say a few maybe provocative things that hopefully will force people to participate maybe. So why C++ in all that case is, well, I think C++, if you use the right libraries, it especially like libtorch, for example, the productivity is there because actually you are actually playing around with Python a lot, so you can easily transfer your code from Python and backwards. You can run simulations in C++ and very easily get them up and running in Python, visualize them, and do whatever you want. We're going to see some examples in a minute. At the same time, with C++, you are left. You have the flexibility of C++. Obviously, all of what I'm going to tell you today, you could possibly do it fully in Python, including writing kernels in Numba, for example. But Numba has some limitations, so it's not C++. Numba has a little bit of C++ limitations, and obviously the code you're going to write, it's Python. You will stay in Python. So if you want then to integrate your code with something else or have some flexibility about the way you distribute your code, you will have to stay within the Python ecosystem with all the sort of maybe problems that go with it. In particular, for example, for me, it's important to be able to integrate my code with Java, JVM, because typically we will process our data and do some analytics in the JVM. So I need a nice integration with the JVM. Yes, of course, you can rely on RPC, and actually in our lab we have a nice project by Fyodor Alex, remind me his name.
You mean further Bukreev?
Bukreev, yes. We had a nice project also called Connector, so do have a look at our repository MIP10PM, which enables you to combine different languages. But sort of this whole story is somewhat, you will have to do something more clever. But if you write in C++, you're kind of, you don't have your hands tied to somewhere else. In particular, if you want to achieve some optimizations that are not possible in Python, you can in C++. And in particular, you can also integrate it with whatever you need. For example, also in physics, obviously people use a lot Giant, Root. Sometimes the whole stack is in C++, so obviously integrating with that will help you if you've written your stuff from in C++ and from the beginning. And that being said, of course, I hope to convince you that in terms of productivity, you're not going to lose much. Okay, so I'm going in the time. Very good. So let's. Are there any questions or remarks regarding the introduction?
Inar dropped an article about using automatic differentiation in astroparticles. I think people could read it later, but otherwise there were no comments. So, yeah.
Great, thank you. Okay, so moving beyond the introduction, what I'm going to talk to you is I'm going to talk a bit more about backward Monte Carlo technique from an even theoretical maybe point of view, and show you two example about how it's used, and then I will dive more into differentiable programming and explain you how even in this sort of two example, which will be related actually in some sense to myography, you can do already cool things. Then we will talk about a bit about the adjoint sensitivity method, why it's important, and how backward Monte Carlo actually opens up that opportunity. So yeah, so what the problem of actually directly applying differentiable programming to simulations, and yeah, so how the adjoint sensitivity method is going to help you. And then I will finish with the last section when I will talk you a bit more about the interplay between Torch, C++, and yeah, and how you can combine Python and Torch in a nice way to solve problems in this area. So let's start with backward Monte Carlo. Okay, so this is a nice picture there. I'm going to show you. So I think in. Okay, so is this. Okay, so let's not focus on the picture for a minute. So what is this backward Monte Carlo technique is doing? So it is all about reversing your simulation flow. So it might happen that the situation you are working in is not in the sense that you have some sort of initial data, and then you have some setup, and then you just sort of simulate you have your physical model, you simulate, you run your simulation through the setup, and then you compare results with what you've seen, so for example, on the detector. Sometimes you want to go the other way around, especially in inverse problems. You're going to see some data on the detector, and then you're not specifically focused on some initial data. You're happy to have a distribution for the initial data, and you want to sort of roll back the whole simulation to see how things evolved from a theoretical point of view. So those ideas are also not necessarily new, at all. Actually, so Laurent Desorgueur and his team have applied those things in Giant, actually, to space radiation problems, to electrons, positrons, yeah, so all sorts of particles. So they sort of called it the reverse Monte Carlo method. And one paper, which is the main driver for us, is the main basis for us, because we are interested in myography, is the work by Valentin Nies and his team from Clermont-Ferrand, and they have really sort of this paper, backward Monte Carlo to apply to muon transport. I think in this paper they actually kind of raised the level about what backward Monte Carlo is. I will invite you to actually have a look at this paper. It's really well written, and it gives you a nice introduction about abstractly what backward Monte Carlo is. So why Valentin Nies and his team who work on myography, and us at NIPT NPM also, why would we be specifically interested in backward Monte Carlo? Well, because typically in I should let me give the thanks to Zhang for this nice image. So basically, because in myography, typically you have your detector, which is basically a single point in space, and then you have the whole flux of muons produced by the cosmic rays in the skies, in the atmosphere, sorry, and they sort of go down, they propagate through the ground, and underground you have your detector. And so if you simulate the whole flux, you just basically you will then to sort of start to fiddle with a way to figure out, okay, what happened on the detector. I should say that there is obviously there are situations specifically within the detector itself that you are maybe in a sort of, in that situation you have a better balance between where the initial condition is and the final state is. In that sense, yes, you will use a forward simulation. I'm not trying to promote the fact that backward Monte Carlo has to be absolutely used everywhere. What I want to say that in this specific case, the muon detector is just a single point over there, and you are going to measure, this is where you measure the flux for the detector. And actually you have a theoretical, we do have a nice theoretical understanding of what at the sort of at the sea level, what the flux should look like from the muons. So the problem here, and it's from the applied point of view, is also very interesting, is because we don't necessarily know what is inside the mountain, what is inside the ground. And so we want to essentially run a sort of inverse problem, tomography, 3D reconstruction problem, where obviously we have some maybe object which is on the way for those muons, and obviously we are only interested in the trajectories which are coming out of the muon detector, because those are the ones that contribute to the flux. And those trajectories, with the simulation, we want to infer about some information about what this object is. So, for example, what is position, how dense it is compared to the media around. And well, that's a typical and nice inverse problem. And of course, you can just sort of so in that sense, backward Monte Carlo actually comes as a natural thing to consider here, because yeah, essentially because of the fact that you are only interested in the final state, and you need to find the flux that has generated this. So it's a backward problem. The flux that generated the flux you actually see. Sorry, the simulation flow that generated the flux you see on the detector. And so that's why there've been a huge progress in backward Monte Carlo, specifically for muons, with an absolutely wonderful C99 library. It's a truly amazing library, extremely fast, that's been essentially built by Valentin. And I obviously invite you all to have a look at this library and see how backward Monte Carlo is actually implemented in practice. What I want to say is to actually talk a bit about, so give you a bit more feeling about what this technique is. in a more abstract way, but keeping essentially this picture in your head, right? So we're going to keep this picture in our head and sort of try to have a good feeling about this what this backward Monte Carlo is. But then maybe I should ask, maybe someone has a comment or a question or some
I
feedback.
will read aloud if everyone has a question. So
please, yeah, Alex, please stop me whenever someone asks a question.
Yes, yes, okay. We can move forward right now. Are you with us still? Okay.
I am. Yes, I'm listening.
No, I said no questions. So please.
Sorry, I saw that there was a question. I was waiting for.
No. I'm just urging to move forward.
So everyone is sleeping after a good meal.
Yes, something like that.
In Europe, in Russia, it's later. You should be already awake in Russia. But in Europe, people sleep. Okay. So let's get a good feeling about what what backward Monte Carlo is. So as I said, we really think in terms of distribution. So you have a distributions of states, of initial states, and you have a distribution of final states, which is generated by some flow, some simulation flow, which depend on some random variable x that is sort of auxiliary to the whole problem. It does not depend on the initial or final conditions. So these states, the states are not necessarily. So in a backward Monte Carlo, it's important to think in terms of fluxes rather than single particles. And in that sense, the state might include all sorts of coordinates, so variables, and it can have positions, coordinates, momentum, direction, kinetic energy. It can have all sorts of other things. But what this position, moment, direction, and kinetic energy that tells you, those are the variables that you actually use to compute the flux. So they tell you that the flux at this position in this direction with this energy is f of s, so phi of s. So that's it's not a sort of, we don't think of it as a particle. We don't sort of evolve this particle like we will maybe doing some forward simulation. No, that's what describes. In that sense, if we go back to the picture, the detector is just a single point in space, and typically in the detector we will measure different angles. So we will have sort of different, so to speak, energy directions. Unfortunately, and that will be a breakthrough obviously in myography, if the detector could measure also the energy, but as far as I know, and Alex maybe might correct, this is not possible. So we just can measure the flux independent of the energy, and we just the direction and just the position, which is the position of the detector. Now, of course, any sort of stochastic flow or simulations flow, so to speak, comes up with the notion of transition distribution tau, and this transition distribution essentially, that's what enables you to sort of, given a flux distribution to at some initial, over some initial states, you obtain a flux distribution over some final states, and that's with this and this is actually going both ways. So this has nothing to do with backward or forward. It's just this is if you think in terms of distributions, you're just evolving a distribution, initial distribution to final distribution. But the good thing about this approach is that at some point you can just put a delta function on your final distribution can be just a delta function, and then you sort of formulate the whole thing now, so your inverse problem as an integral, where you're really integrating over the initial, you sort of a distribution of initial states, and then you look at their probability of reaching your final state, and that essentially sort of, this convolution will tell you what the final flux is. And backward Monte Carlo is all about evaluating this integral. So if the flow were actually invertible, so if the flow were actually invertible, so then it's pretty easy, because if I give you a final state, but well, it's simply a change of variables. So you just need to map so you sort of, with the flow, you push forward the distribution of initial states down to the final state. If the map is invertible, you get a flow backwards, and you simply, whatever your final state is, you pull back it to the initial state. And then you have normally the whole point is that we have a very good understanding of what the flux initially was, and then your model tells you, well, what was the probability of going from those initial states down to your final state. And this integral can be simply estimated by simple Monte Carlo. And yeah, so, and the whole point is that you're just generating those auxiliary variables that, so to speak, they give you different trajectories that could be taken by various particles. So that's the sort of way to think about it. But in practice, those random variables really enable you to kind of generate a distribution, initial distribution that you can use to evaluate this integral. And obviously then the weights, well, what the weights are, obviously they are just a change of variable. So they are just a determinant of the Jacobian of the inverse map. So if this thing is well defined, then it's just a question of changing variables in this integral to be able to move from your final state back to your initial state. Are there any questions about this sort of basic? Because if this sort of doesn't make sense, then the following thing will not make sense.
No questions so far. I think we can return to it if there are some questions.
Okay. Obviously, in practice, there is no way to compute the whole flow. So in practice, you will have little small flows that you use. You break down your flow into small steps that you actually invert. And if obviously every single step is in variables, and you can simply invert and then keep on sort of changing variables in your integral until you actually obtain the final, you reach the final. So typically you are sitting on at your detectors, then you move a little bit, you say, okay, so that's my, now I have to estimate the backward flux here. I have a distribution for my final flux there, so I move a little bit more, then I have a distribution, and then I move up until the case where actually, okay, the distribution of the flux I managed to obtain, actually I know what it is, just theoretically. This fermions, there's this Geisner formula or corrections of it that enable you to finally say, oh, okay, that was the flux. And those then, oops, sorry. Those Jacobians, well, this is just the general. They enable you to compute the weight. So basically, essentially, if you know how to do it for one step, then you easily know how to do it for many steps. Okay, now the real life comes in, and the real life is all about, I'm doing on time, sorry. Yeah, I should speed up myself a little bit. The real life is the fact that you actually can't invert typically this distribution, and we use this technique is not necessarily related to backward Monte Carlo. This technique is basically always used everywhere in any sort of serious evaluation of integrals, because typically you want to evaluate your integral with respect to a much better behaved distribution than what you have, and then if you've chosen your distribution such that the what's called random Nikodym derivatives. So the random Nikodym derivative, this is a mathematical term. it's essentially the ratio between two probability measures or probability distributions, and obviously this ratio has to make sense. In particular, if that thing is 0, this has to be also 0 for this thing to be well defined. So if you've chosen your distribution correctly, so that then you can just simply evaluate your integral with respect to the new distribution that you actually understand better or is better behaved, and then you just have to reweight the whole thing to get your value of the integral back. In practice, this means that you have to come up with a nice backward flow, and here this is the hard part. So we're not going to touch upon this because this depends on every single concrete problem. Even within muons, there are some decisions that you have to make about how you construct this phi, this biasing phi, the regularized version of the flow backwards. And in our case, that has been solved in some sense, at least for this type of problems, by Valentin and his implementation of muon transport in C99. So that's why this sort of paper is important. For us, we are gonna just to sort of move on with the toy example where we sort of assume that this thing has been computed for us. But yes, the whole clever part is about being able to come up with a good PV, and this determines whether backward Monte Carlo actually can be implemented in your case or not. One special case actually of biasing or trying to come up with this thing is actually which is of interest for us, because I remind you that, okay, so sort of the main example I want to run through is the fact that we don't quite know what this object is. In particular, what we don't know, we imagine that this object, so we imagine that the ground is made out of some material, so some standard rock with sort of constant density as is, and this object is made out of some other material, which, for example, is very hard for the muons to traverse. So the muon will have higher probability to decay here and reach any state over there, passing through this object, than it will have through passing through standard rock. And so understanding where exactly this object is and how dense it is, so how much of a mix it is with the other object with a standard rock behind, is what our inverse problem sort of is, and this is what we want to solve, because given our data in the muon. So that's how myography is formulated. The thing is that typically in the forward case, what you're gonna do is you will have your tau will be a mix of taus, where this tau is sort of this transition density, as I said, is either the one of the standard rock of the object or of the object. And when you forward simulate, normally when you move inside the point here, you're gonna choose at that point with a probability whether you're gonna the next step is gonna be with the material of the object or with the material of the ground. And this in a forward simulation, that's the natural thing to do. And this probability is exactly the parameter we're trying to understand. So at every single point in our space, we're trying to understand with what probability you would have chosen to interact with the object rather than with the ground. In some sense, how dense this object at that point is with respect to the standard ground. And in mathematics, we call just this sort of thing a partition of unity, meaning that at every single point in your space, you're either saying, okay, you assign sort of probability of moving with one object or the other. And when you move forward, then it's very natural. You just at every single you move, you're at some state and you choose with which material to interact. But when in a backward simulation, you don't know where basically where did this thing came from. And here comes the story is normally you will introduce a biasing partition of unity. So typically in myography in the Pumas code, this will be actually taken to be the probability of interacting with the object at the final state, not at the initial state, at the final state. And then you sort of propagate it. So you choose with object you interact, you move backward, you use the flow related, associated to this object, and then you simply correct it with the actual probability. So that's exactly this biasing technique, but working sort of in this particular, sorry, this is a typo here, should be L, comma B, but I'll correct it later. But that thing actually is particularly nice for us, because later when we will apply, when we try to integrate our automatic differentiation engine with the simulation, that P, so basically we will want to sort of differentiate with respect to the PLs, basically with this unity, because that's, well, why we want to differentiate, because we sort of have to learn this parameter, sort of learn. We want to find the optimal partition of unity, which makes the data that we see on the detector the more likely. And obviously you can just sort of try various values of, try various partitions of unity, but obviously as the object gets bigger, you have a more complex, this is a very high dimensional problem. And when you try to run optimization in high dimensional problems, or inference, for example, we are very interested in running Bayesian inference on this type of things. You need the higher order information, gradients, Hessians, and third order information. It's very important. Otherwise, you just end up with a whole range of efficient optimization and inference algorithms is simply close to you. You just can't use them, and which in many cases just makes the whole problem computationally unfeasible. And the whole sweet thing about this approach will be that some of those things will work. Okay, after 1 hour of blah blah, I will manage finally to run some code. Let's start with some Python. So my partition of unity, so baby example, there will be no crazy differential cross sections yet for muons or whatever. We're just gonna sort of have a toy example trying to follow this picture. So we're gonna put our detector at the origin, right? And there are just having a Gaussian for this object. So the Gaussian obviously will, at the center of the Gaussian of this object, we will force the flow to interact with the object with probability 1 away from this center. Obviously the Gaussian is decaying very fast. We will control how fast it decays. We'll also control where the center of the Gaussian is. But away from this, obviously the probability of interacting with this object is much smaller. So that's basically the basic setup that we're trying to sort of emulate. It's very close to real. So the real life setup we're working on currently is sort of close to this one, but obviously for the purpose of a tutorial, it will be nice to do. And welcome to Pytorch. So Knode will be just a the information. So those are the 3 parameters which encode what the Gaussian is. So the first 2 variables obviously tell you the coordinates where in 2-dimensional place. 0 the x-axis, 5 the y-axis, all centered at the detector at 0, and 10 gives you basically the concentration. So for example, in a minute, I'm gonna show you. Okay, so the probably is a nice. Okay, so I have a picture for you here. Essentially, my detector is at the origin, and those lines are just the level sets of the Gaussian. So essentially, if you're here, this is the center, okay, not the center of the Gaussian. The material is highly dense, you will interact a lot with it, my object, and somewhere over there or near the detector, the interaction with the with the object will be considerably less, and we will mainly interact, say, with the standard talk. Okay, so here's your formula for the mix density. So sort of this is a partition of unity, sort of to speak. So just we are starting to use some of the API to kind of have the spoiler. Differential programming is about sort of writing your software in a way such that every single execution can be differentiated by your software, so that for free, so to speak, you get the gradients and even higher order derivatives of the calculation you're doing. And Pytorch is built in such a way that all of those operations that I'm doing, including setters and getters, they're all actually part of this sort of. They're all sort of differentiable, so they also have derivatives. Unfortunately, Pytorch doesn't have a pi, despite being such a huge framework. But the idea here is that I'm taking my mix density, and obviously, that mix density is essentially the level sets of that. I'm just summing the squares of the coordinates of the center with respect to the point I'm looking at the state. So yeah, so the state in this case is just the positional, so to speak, the positional thing. The direction is also obviously there, and the direction is given by theta. We are going to think about three different angles for theta. So theta is the angle at which we measure the flux at the detector. So we are just going to take, and theta will be the angle with respect to the y-axis. So we're going to take one which points here, there, and a bit less there, imagine. And now comes, so basically the backward Monte Carlo implementation. Okay. So before I run through this backward Monte Carlo implementation that I'm gonna execute, because otherwise I will not be able to do your report for you. So for example, if I run this backward Monte Carlo implementation, oops, sorry. Oh, I'm sorry. Where's my GPython? Okay, I'm sorry. Here this backward simulation. So that's the result. We're gonna go through the code in a minute. So as I said, we have three directions that we measure at the detector for the flux. We measure, and then we sort of simulate two steps backwards. So we simulate a bit here with various lengths, and we simulate then the particles a bit further, where since the flux, we measure flux at this angle, it has to enter at this angle, but then the next step it can start to deviate. And this is a simulation, a two-step simulation for the backward Monte Carlo for the particles in all the thetas. So this code is just plots this step. This just executes the backward Monte Carlo. The more interesting code is the simulation, and the main objects in Torch are tensors, as you've seen. An example of a tensor is, for example, our theta angles. Sorry. So it's just a tensor. The tensor can live on CPU, it can live on GPU, it can have a type for the data it has. It can be float, it could be a double, it could be an int, whatever. You can send it to Cuda if you have Cuda. So this tensor sits on the Cuda, so this operation obviously returns, and tensors typically have a buffer inside them, and typically they copy data only when they have to copy. So most of the time.
Could you explain what does this operator does? Does
Cuda.
it? Yeah, it copies,
yeah, it copies the data on the CPU to the CUDA device number 0.
So then it could be accessed.
That thing sits. So if this is T, then T sits on the GPU. It is different. The CPU itself, it is stayed where it is. I mean, I haven't touched it. That's
I see. Thanks.
The whole point is that you can write simulation code using tensors. It's really nice because basically, if I want to compute the rotation with respect to a theta, right? So the rotation is when I stay on the detector and I want to move backward at some angle. And the nice thing is that this torch cos is a broadcasted operation. So, for example, the torch cos theta. That's right. So at every single theta, so I've chosen obviously the theta which points horizontally. Obviously, it's cosine 1, and then it. Yeah. So the point is that this thing is efficiently mapped through all these values, and then you kind of can take a collection of torch tensors and stack them together into a single tensor. And obviously, at the end of the day, you will get sort of for every single theta, you will get the rotation metrics sort of batched together into one single tensor. And I guess I think that's sort of a cool way to kind of formulate your dynamics of your the dynamics of your simulation. Yeah. So to use broadcasting. So in particular, we take a number of particles, right? And then here we are going to generate a tensor for this amount of particles, and we're going to run our calculations on top of that tensor. And we're going to, obviously, at every single step, we're going to stick with this tensor and apply operations from torch to it, such that this backward MC can be then differentiated. So this will be an example of a differentiable programming routine, because every single step can be differentiated with respect to a parameter. In our case, the parameter is node. So not sort of this is the tensor which encodes my partition of unity, essentially. So it's the origin of the Gaussian and its sort of dense sort of curvature. Okay, so initially, as you can see on the picture, I just need to move a random length backward the particles. So I just generate a tensor, move, rotate, get the rotation by theta. Then so this actually sort of this is essentially saying that I'm not moving with the x-axis. I'm moving length 1 with the z-axis, and then I just broadcast by the number of particles. I broadcast the rotation, and I take a matrix multiplication across this whole sort of tensor of particles, and then I just simply add it back to the detector. Again, the detector gets what's called broadcasted, so it's added to every single. So the detector of the origin is added to every single vector here, and the vectors are kind of stuck together into a single tensor, and the rotations are matrices which are also stuck into a single tensor, and those rotations are multiplying every single vector. And the way I force it to sort of run the right way is by reshaping, so to speak, the tensor in a way so that it's sort of clear to Torch how to run this multiplication. So that's the sort of I hope I'm fine with time. That is sort of the way you sort of run your program. So you sort of start with a tensor and then you simulate the float backward. Again, this is a toy example, but it's very close to what happens in myography. Then actually those coefficients, material A and material B, I've just again taken something for this toy example, but the whole point is that going through material A is sort of much harder than so going through material A is your sort of standard rock. It's easier than going through material B, which is actually your object. And those coefficients are essentially, in your formulas, they're essentially the ratios between tau L naught and tau L naught biased, right? So that's so tau L naught, the probability of moving from some initial state to the final state will be much smaller in material B than it will be in material A. And that's the whole point. And essentially what I'm trying to do is then I'm trying to compute the biasing, and as I've said you, in biasing I have to choose one of these probabilities. I have to choose with which material I'm going to interact, but I'm choosing it with respect to the biased partition of unity, so to speak. And in this baby example, small example, I'm just assuming that it's 0.5. So my biasing partition of unity, so to speak, it's a constant. It's at every single point I'm going with the base material or with the object material. I don't know. I don't have any view on this. It doesn't necessarily work this way properly for real life, but in our baby example, yes, that's particularly fine. So I'm obviously generating a bunch of booleans essentially. So it's integers between 0 and 2. So actually 0, 1, 0, 1 for a single particle, and then basically with probability half, I'm picking one of the materials, material A, or I'm picking material B. Sorry, just and then this is this sort of the biasing Jacobian. Again, this is, don't pay attention. In practice, you will have to compute obviously these numbers properly using differential cross sections in all the simulation machinery. But for our case, we're just gonna have something which depends on the length how you traveled through another Gaussian. This is not important. The whole important is this operation in Torch, which takes a mask. So a mask is a set of booleans. So here I'm just taking, okay, I'm filtering through all the particles which are going to go with material A and all the particles which are going to go with material B, and then I obtain the weights. I calculate the weights. Those calculations are exactly the ones I've shown you in the formula here. So yeah, so it's either this one or the other one. And obviously here we use this function called mixed density, which is the real partition of unity that we don't actually know, but in that case we sort of set up this node. We use this material density to sort of compute it, and the final weights, depending on how biasing went, will pick up this tensor or not. So that was the first step. The second step is very similar, apart the fact that now I can have some randomness. So there is some randomness now with which I generate rotations where the particles can go, but the principle is the same. I generate a vector going upwards of a random length, then I randomly a bit send it. Again, all of that generating sort of this is related to the continuous energy loss. So this has to do with the energy. So how far in column density you can go. Obviously, there are cross sections for it, like Bremsstrahlung, Perk production, all that stuff. And then for the rotation, normally you are using Molière theory or corrections to Molière theory. again, this is a baby example. I'm just picking some numbers which sort of look like the real life. In practice, you will have to write what's called torch operation, tensor operations, which will compute for you those rotations. And we're going to see this in a few minutes later. But for this baby example, the principle is that this whole calculation, again, follows the differential programming paradigm, in the sense that I'm only using the operations provided with torch, and those operations are sort of at every single step. I will be sort of keeping the information about the derivative of the node. So each time I'm using node here, for example, so here I should have computed the derivatives. Here it's a new function, so it keeps track of the derivatives there, and the automatic differential engine will then sort of go backwards to compute the gradient when I need it. So yeah, so that function sort of enabled us to sort of have a baby example of a backward Monte Carlo simulation. Are there any questions?
I do not see any questions so far.
Okay. Okay, then let's move forward. I'm doing fine this time. Right. So the whole point was that, yes. So at the end of the day, you get this picture, and normally you carry on. So you carry on. So for example, obviously compare it to that picture there over there. We're somewhere here, right? Or here, I don't know, somewhere here, and then it's sort of this thing has to move, bam, 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 bam. You do many steps, and you reach a level where you actually have, you know, what the flux of the muons is. In our case, because it's a tutorial, we're gonna stop after 2 steps, and we're gonna assume that we actually know what the flux here is, and we actually know that the flux is just 1. So let's assume that so over this region, for some reason, the flux is just 1. I just don't want to sort of mix it with other things, so it's a simplifying assumption, which has nothing to do with reality. But normally, as I said, you should have been carrying over the simulation. But here we just stop there, and obviously now, if the flux were 1, then we're just summing the weights. So we will have to simply sum the weights, take the mean, sorry, for the weights, and obviously we can compute it. And because we sort of get what we sort of expect, the flux being a bit bigger on the sides, because sort of to go from here to here, you interact a bit less with object than to go from here to here. So yeah, so that's a little illustration in Python of a backward Monte Carlo procedure. Let's now move to differentiable programming. Okay, so for differential programming, normally you come here and you see your flux and you say, okay, so that's my flux. But normally in practice, right, you're gonna see some flux on the detector from the actual physics, so the real thing. Here again, I've chosen some numbers a bit sort of randomly, but I sort of want the flux to be sort of a bit less on the. I want the flux to be a bit smaller on the left than on the right. That means that the object has to sort of move a bit. So the real object sort of has to be somewhere over there to sort of have this direction to get less flux than those directions. Let's sort of play this game, and the aim of the game is to really to figure out, okay, what this value is. So what is the optimal position of the flux is? What the optimal position of the flux is? What is the optimal position of the node, the Gaussian is of my partition of Unity, so that my simulation actually fires something out which resembles the thing we've seen on the detector. So for that, we can define the log likelihood. Again, this likelihood is just gonna sum overall for every single theta, the flux we observe. We compute the backward Monte Carlo, and then because it's a Monte Carlo simulation, then obviously the flux is supposed to the mean. So that's the mean. So the distribution is supposed to be a normal distribution. But because it's a log likelihood, I don't really care about the any constants I'm going to run on optimization, so I just divide it by 0.01. But obviously, the longer you run, obviously the backward Monte Carlo simulation, normally if you've done everything right, your samples are going to be independent, and obviously your estimate of the flux should be quite precise. But in our case, we don't really care about that. And here comes the sort of the sweet part of the differential programming, is that I can evaluate now the gradient with respect to the parameters of the partition of unity, so the parameters of the Gaussian. So what happens actually? So normally I have to tell Pytorch that I require the gradient for this tensor. So what it's going to do is going to take this tensor and it's going to create a program inside Torch, which takes this tensor and map it to other tensors, and we'll have some sort of execution graph. And if I tell you that I need the gradient, it's going to build this graph with respect to this stuff, with respect to the leaves I compute. So for example, if I have a Torch, some random tensor here, sorry. So if I have a random tensor A, I can require the gradient for A. Then it's going to tell me that it requires a gradient. And so basically every single torch operation on this tensor is, including multiplying by other tensors, for example, multiplying it by some other tensor, is going to be recorded into a graph up until you actually sum. So you see multiplied backwards. Sorry, so I've summed the tensor here. If I sum the result of this graph, then I get another function called sum backwards. So it sort of records every single operation I did on this tensor, and those operations are later enable me to run this torch autograph engine. So I sort of start with some node parameter. So detach means I detach. So if node parameters for some reasons have been attached to some other graph, I say no, detach it. So give me a reference to this tensor. This operation actually doesn't copy the buffer. It doesn't copy the data in the tensor. It just creates another tensor on top of that data, but which doesn't belong to any other graph. Because if the tensor belongs to some other graph, then what Torch is going to try to do is sort of combine all of this into a huge thing, and then you don't. When you compute the gradient, you will get funny results. We don't want that, so we just detach, and then we require the gradient again. So we start from 0. We have a node params tensor. We require the gradient. We simulate now. Given this tensor, we run the whole backward Monte Carlo simulation. Because our backward Monte Carlo simulation is essentially a differentiable programming routine, differentiable programming program, in the sense that every single operation I have used here on the tensor node, is actually compliant with the graph. So compliant with operations that Torch can differentiate. Obviously, you can also actually add your own operations, but in this case, it was important to kind of run it. So yeah, so that's what sort of differentiable programming is all about. It's just writing your program numerical calculation, which is conformal with whatever the rules are of your autograd, or whatever your differentiable programming engine is. So because I I was sort of careful about doing all of that. I can evaluate now the gradient, and the gradient is now evaluated with respect to the node here. And for those of you, half an hour, for those of you whoever tried to, who read, so maybe if some of you have computational finance, background, or try to apply automatic differentiation to simulations, and if you read this paper, basically to apply the automatic differentiation, it will pathwise, because what we're doing, we are differentiating every single trajectory pathwise. It was important to actually introduce a biasing method, because if you start to differentiate with every single step, then your graph is going to explode. So normally you should not differentiate the measure. So the flow, you should never differentiate the actual flow. So the flow phi shouldn't be differentiated, because this will create a problem you won't be able to handle. What you're instead doing is, again, as we've seen, biasing techniques enabled us to actually invert the flow itself, and now biasing techniques also now enable us to actually compute the gradient, to move the gradient inside this expected value, essentially. So that's an important point. In a sense, we could do that, but it enables us to do something which is computationally feasible. Otherwise, it won't be computationally feasible. So again, as I said, that's what I was alluding to in the introduction. A lot of techniques that have been sort of developed to make backward Monte Carlo run and are actually very close to what people in differentiable programming are trying to do. So the tools are basically there. So here we got actually something for free, and we got the gradient. And obviously, you might want to look. Okay, so what this gradient looks well. Oops, sorry, why? No, sorry, what I did. I probably won't. Okay, thank you. I think I've touched something, but no, it's fine. Yeah, so here is a gradient. Obviously, for this is a number of steps I'm simulating over, and this is the value of the gradient with respect to, I think, with respect to no, with respect to the first parameter. Okay, so it's with respect to the x-axis. So it's with respect to the center of the Gaussian, and I take the x-axis. So it's actually the most interesting gradient, because situation, because I am trying to move the gradient to the left. Yeah, and so I sort of initially this doesn't sort of converge, but then after a few steps this actually does converge. So maybe I've done something silly, but yeah, let's carry on. If I get crazy results, then I will just rerun the notebook if I touch something. So what does this enable us to do now? So we've built our log likelihood now for the flux, and we can easily evaluate its gradient. So what we can do now, well, we can sort of find the optimal values for the log likelihood to have the highest probability for the flux we observe. And I propose you to, in this situation, is a baby example. We're just running things. Let's run just a stochastic gradient. It's a genuine actually stochastic gradient, because the value and the gradient are actually stochastic. So it's not just the fact that you're actually getting a batch from somewhere. Those things are actually stochastic. So for initial value I take 5, 5. So I'm just moving it somewhere to the top, to the right top, and let's see where it's gonna move. I hope actually I haven't screwed up something. It will try to move it to the left, back to the left. So the code for the gradient, stochastic gradient, is a typical one. I take the node, so I have the initial node, and I move the node is the parameters of the Gaussian. I just move them by some learning rate, saying in machine learning terminology, by the gradient. So nothing clever. I just move it, and each time here I just typically I want to prevent it from sort of firing above 1, because I'm not interested in that. In most actually stochastic gradient technologies, machine learning sort of have some sort of momentum information coming from the norm of the gradient. Yeah, it's fine. So you see the log probability keeps reducing, and we are kind of ending up somewhere to the left. So let's just plot the graph of the log probability. So yeah, initially it was pretty big, and so the problem has been sort of has some actually has a sort of valley where when the thing falls, it basically starts to converge. If we move towards the end, zoom towards the end, yeah, so we sort of have, as I expect, past 50, the last past 550 iterations, we sort of have some sort of convergence for the log probability. And the optimal node, it makes sense to take the expected value over those last variables, and so basically I'm seeing what I'm supposed to see. So the object is a bit to the left, so you will have less muons, so less particles coming from that side than from this side, because object obviously it's harder to penetrate for the particle. I mean, the problem has been formulated in such a way that this is what it's not just stochastic gradient descent. Obviously, if you formulate your problem using differentiable programming, then you can do wealth of new information, new algorithms you can use, including, for example, running Bayesian inference with Hamiltonian gradient, Hamiltonian Monte Carlo techniques, where you need sometimes not even the gradient, but actually higher order derivatives. And this is a current research for us, is that we actually try to figure out the right stochastic Hamiltonian gradient, stochastic Hamiltonian Monte Carlo technique to be able to run things specifically coming from myography. Yeah, are there any questions?
Okay, no questions, and we are nearing the end of our time, so we have only 20 minutes.
I have 20 minutes, right?
Yes, and we will probably have to leave like 5 minutes for next speaker to prepare.
Okay, 15 minutes. That's good, because I want to talk about So okay, so unfortunately I don't see the audience or anything, but in fact, all of that stuff that I've run here can be run for a forward simulation, and this is exactly what is actually in the if you read the Mike Gill's paper about algorithmic differentiation for simulations in computational finance. They run it. They use a biasing measure to evaluate the gradient for the simulation, and then it's essentially a pathwise integral. And it's obviously in finance they run a forward simulation. And so everything I did actually in this differentiable programming section can be run for a forward simulation. Is that a good thing? Is this good news? So does anyone has any comment about that?
No comments. I think people are a little bit out. Maybe there are some kind of comments about the technique or installation or whatever, how to do these nice things yourself at home. And Roland probably is not asking never to do it at home. On the contrary,
Yeah,
should
we'll
try to
make
do
it
it at home.
more easier. Okay, so no worries. So no question. So the answer is that it's actually bad news, unfortunately, because if you run a forward simulation, even if I've told you that you've been careful enough to move to a Bising measure, here, and to avoid explosion with respect to the flow, your algorithm, because it has to take the whole trajectory and differentiate it. So you have to simulate the whole trajectory and differentiate it. So this is parameter n, which actually in every simulation is going to be n is potentially very large. So the number of particles is large, of course, but the number of steps, this is what actually controls the precision. So because if you do smaller steps, then your simulation is more precise. I mean, it's more accurate. You can achieve accuracy through reducing the step size. So if your algorithm depends in that case rather badly on the number of step size in your evolution, then this algorithm is somewhat hard, and then that's probably why also algorithmic automatic differentiation haven't been used in industry, but rather in rested on the paper. But if we go back to ODEs, then there is an efficient way to compute the gradient of a loss function. So if you have if you have an ODE, right, and we evolve it from time 0 to time 1, and then we have some function L of this ODE of the final. So it's like a bit like we evolve. It's like our simulation flow, and at the end we have a detector, and we measure the flux, and we have the loss function being essentially the sum of the gradients of the errors. Then I want to differentiate this expression with respect to theta, and theta in that case parameterize your dynamics of the VDE. Then there is a very efficient way which goes back to Lev Semyonovich Patragin, and you can read it in his book in 1962 and his collaborators, which actually ask you to define what we call an adjoint, which is essentially the gradient of the loss function with respect to the solution at time t. And this quantity actually solves a backward ODE. So backward ODE doesn't make sense. ODEs you can flow any way, any direction, there's no problem. But the point is that this thing is gonna satisfy an ODE which actually starts from the final condition where you actually know, of course, what is DL by dxt1, because it's just the function itself, but you don't know what DL by dxt0 is, because you have. So what we have done so far, we've been taking the gradient inside this integral. So in this implementation above, but here there's a much more efficient way is actually to evolve the gradient. To have another ODE, and that has been exactly used. That has been exploited by Chris Chen and Ricky Chen and Chris Rakauskas in their papers. Is that those gradients are actually solving some other ODEs or differential equations, but moving backwards. And amazingly, this also works. So the way we simulated the backward algorithm also enables you not to evolve the flux backward, but also to evolve the gradient of the flux with respect to the parameters, or the gradient of the gradient of the flux, because then you know the gradient of the flux, then you know obviously the gradient of the whatever your loss function of the final flux is. And so essentially, if you go back to your algorithm, then you're to the backward algorithm, then it's easy to figure out how to evolve a gradient of this phi, the gradient of phi, with each step independent of n. So not independent of it, but accumulate the gradient, so to make it evolve with the whole evolution. And actually, here I did the good task of actually reproducing the whole backward Monte Carlo simulation in C++, and you can see that in basically the same code. Sorry, so that's, I should have had this here. So essentially the same code as we had in Python moves to C++, but the good thing is that, so basically word to word. But now, of course, instead of taking the gradient with respect to backward Monte Carlo, I'm going to evolve both the weights, so the flux, the weights, and the gradient. And what happens is that I'm only applying the moment I have to compute the weights, I just compute the gradient with respect to this biasing step, to a single step. So I compute the weights and I compute their gradient and I accumulate the gradient. And then when at the next step, because it's a backward Monte Carlo simulation, you can't do this in a forward simulation, but in a backward simulation, the next step when you have to compute the gradient, you only call the autograd engine only on the nodes, only on the tensors which have been used in this particular step, and then you use the product rule. So the gradient of the product is the gradient of one term plus the times the term times the gradient of the previous term. So you simply accumulate the backward Monte Carlo gradient, and it's essentially, this algorithm is more or less the same thing of Pantragen's evolution of the gradient. So you sort of, and you can, and it doesn't stop here. You can evolve higher and higher order derivatives. So that was the gist and of the whole talk in some sense. And then, not much time I left. A little bit, 10 minutes, right? This thing enables you to actually, so I can run it, and because I've set the seed fixed, you can see that this thing completely agrees. So that's the backward MCs in Python one, where I differentiate pathwise and apply the gradient, and this is obviously the gradient I computed, but now it's constant in the number of steps, which is an important point slide, and this is what I meant. Then, despite the fact that the evolution itself is much more complex in physics, the understanding of this evolution and the techniques we have to run this evolution through the backward, through the developed methods of backward Monte Carlo, enables you to actually run and compute gradients in a way which is actually even more efficient than what almost essentially as efficient as you will do for an ODE or stochastic differential equations. And by the way, we don't even have this in partial differential equations, which is another term of interest. You wanted to see the installation in a minute. So how? So this, what happens is that you can simply write your C++ function in a normal way. So you just write your, so here are the C++ functions that I've just shown you in the notebook. And then Torch, if you include your Torch extension header, It contains a copy of PyBind 11. So that's an important point. If you write C++ using libtorch, please don't use your own PyBind to integrate with Python, because this will come in conflict with what Pytorch uses. So Pytorch has its own copy of PyBind, and you get it for free if you include this header extension H. And then there's a helpful function to create your PyBind 11 module, and you, as typically in PyBind, you pass in the reference to whatever your function is, and then you will be able to, when you run this load module, it will be able to pick up those. It will take the source file and whatever the includes are, because I'm using some of the other, and you can specify some custom compiler flags. I use C++17, so this will compile it. You can do the same thing for kernels. In my case, I actually have written some kernels specifically to compute some of the differential cross sections, for example. It's the same thing. So but you just put it in the CUDA source file, and again, Torch, basically Torch has its own Ninja, also important, and it's gonna build it for you, and you can specify the extra CUDA flags. In my case, I use typically CUDA lambdas and C++17 within CUDA. Also, I have to specify that it doesn't come for free, and it's gonna compile it, and those functions are in fact available to you. They are in fact available to you as normal. So diffpms CUDA is your now module, and the function is available to you as a normal Python function. The cool thing is this line, pycall guard release GIL. So that means that there's no fishy things going on with libtorch. It's a fully C++. So you are talking to the C++ backend directly. There's no Python hidden or anything. So you can completely release the GIL and do whatever you want. In particular, so for example, I implemented the Bremsstrahlung differential cross section in C++. I don't have time maybe to talk more about it. But the thing is that you can extend Torch, because in C++ to run it, to run those kind of calculations, because as I remind you, here I was multiplying by the Jacobian, and I was computing the rotation, say, matrix and the transport, right? Here, so here, essentially, I'm doing a transport, and here I'm essentially multiplying by the Jacobian. All of those things are actually heavy. They depend, as I said, on modular theory, and they depend on the energy loss theory for whatever particle you're running, and those are heavy calculations. You can implement them in Numba, but as I said, you kind of put yourself if you implement it in Numba and you integrate it with Torch, that way you stay within Python, and that will bite you later. Instead, I invite you to actually implement it. As you see, it's very easy to prototype and then write C++ code. Implement it in C++, and then run it on in Python if you need a more friendly framework. To say the last thing, the way you could go about writing your kernels is that you have in Torch access to, in Torch you have direct access you have a direct, so given a Torch tensor that I call result, you have a direct access to the pointer, to the data behind it. So at some point, if you really need to just, if you don't want to use, because you do have an overhead if you use the setters and getters of the tensor and all that stuff, if you just want to run a calculation, you will get the data pointer out, and then you're in simple C here. So you just run the, so for example, this function implements, it takes a lambda, a C++ lambda that I want to run on every single element of a tensor, is then what I'm doing, I'm just getting the pointer out, and then I'm running, looping through, applying the lambda to every single element in the tensor. So that's the important thing. Another important thing is this data pointer actually is a CUDA. If your tensor sits on CUDA, then actually you can, you're actually getting a CUDA GPU pointer. And in that case, again, if here I get the GPU pointer, and then I define a kernel, this time a CUDA kernel, and then I launch this CUDA kernel on this pointer on some device. And again, I'm using a concrete sort of, I can apply this the kernel on CUDA, and so therefore there's absolutely no overhead involved coming from the C++ front end of Pytorch. So that's the way actually we manage. So the only problem is that obviously those operations that we write on tensors, they are not conformal with the differentiable programming. But as I said, you have to sort of you can make those operations. There is an API, but I don't have time to talk about it. To define a derivative for every single operation you write on a tensor, so that it's conformal to the Pytorch autograph engine. But somehow I hope that I convinced you that with this automatic sensitivity method, that sometimes there are more clever ways to compute the derivative, and you don't necessarily want to integrate with the whole autograph engine. But the reason is that why autograph engine is actually important and helps you is that this parameter theta, you can have an actual analytical function that you can't integrate by hand, or but then you use the autograph actually to compute this part, essentially. So the sort of the conclusion of the talk is that we, in physics and in numerical analysis, we have clever ways to compute derivatives, but the autograph engine enables us to actually take it to another level and have more complicated functions depending on theta. Because obviously I don't want to be sitting here. It's easier here to compute, maybe because I have a Gaussian. It's easy to compute this derivative by hand, but in practice I might not. My partition of unity can be parameterized by a really crazy function, and this autograph engine will actually pick up the gradient for that crazy function. But as far as the simulation itself is concerned, then I have a more clever way to compute that derivative. So it's really an interplay between between the autograph engine and whatever tools you have available through the algorithms you build. So it's all in all, it's a really fruitful field, which opens up.
We actually have a question. We only have 2 minutes left, but we have a question from Bulat. If a simulation flow is not inevitable, does it tell us invertible, not inevitable, invertible. Yeah. Does it tell us something about the data, or it's mainly because of inverting operation?
No. It's just in this case, it's it just has to do with the dynamics. It has to do with the dynamics. In fact, the easiest thing is when the probability of getting from your initial state to the final state is 0, for example. Then you have to use.
Actually, there are a lot of questions there because this particular point is complicated. There are principally uninvertible processes, and there are instabilities as well. I'm not sure we have time to discuss it properly, but
this is why you introduce a biasing technique. So it has to do with the dynamics of the flow, and this is very specific to the problem you use and the assumptions you make. So, for example, Pumas, Valentin-Nies, in his implementation of Humus, made some various decisions about how he evolves this flow. which part he inverts. Sometimes he adds a back in the background another process to make some of those processes invertible. So it's a very complicated story. So yes, this story is not about tools that you can just simply take and apply. So you will have to design the whole. First, the success depends on you being able to design a good backward Monte Carlo simulation engine.
We do not have a lot of time. Maybe a one short question or something like that. And of course, we will be having seminars on that in future, and we can discuss it in more detail. Okay, I do not see any questions. Of course, you can later ask questions in the Zoom chat, and we can later discuss it in Telegram or in any other platform you want. Yes, Roland, thank you very much for your report. I think not a lot of people understand fully what you were trying to tell, because it requires some knowledge of the system, some knowledge of the, even I'm not sure a lot of people here understand here when you talk about GIL in Python, what it is. It's a global interpreter lock, and I'm not sure anyone understands that it is, but still it's very illuminating. And we are moving to the next talk.